Hey all, this is Barry, and I'm here to teach some physics. These videos are meant to summarize a unit, and today we're hitting the dynamics unit for AP Physics 1, including Newton's laws and forces. Let's get to it. First thing we need to do is make sure we can define a force. A force is going to be defined as a push or pull on an object due to its interaction with another object. And you see for both the push happening here and the pull happening here, there is an interaction between the two objects as they actually meet and touch each other. This is going to be true for any force that we have, and the interaction can be different based on the way that objects are different, and those interactions between them will vary clearly. But it is important to note that there does have to be some sort of interaction between objects for there to be a force present. Next thing to look at are Newton's laws that originally defined forces for us. He has three laws. The first, body at rest will remain at rest, and a body in motion will remain in motion unless acted upon by an external force. It's very important, and we'll get to some of the brief definitions of these in just a moment. The second law, it says that the force acting on an object is equal to the mass of that object times its acceleration, or F equals ma. And then finally, the third one, for every action, we have an equal and opposite reaction. In summary, we can say that the first law is the law of inertia, and you'll see over here, inertia is defined as the ability of an object to resist change. For early physics, especially at this point with what you've learned so far, we're essentially going to define that as mass. The more mass something has, the more likely it is to resist change. Just because it's bigger, the less mass, the less likely it is, implying that it's easier to move. The second law is summarized as F equals ma, and that's really the most important part there. It's written out as the whole law, but the important thing that we gather from that is that the force is going to be equal to the mass of an object times the acceleration of the object. And then finally, the third law is summarized as action-reaction. For every action, there's an equal and opposite reaction, opposite just being the other direction. As we've talked about with vectors, it's going to be the same magnitude, but the opposite direction it's acting in. Just to make sure we note before we move on, force is going to be represented with that F and measured in newtons, capital N. M, mass, is going to be measured in kilograms, kg, and A, acceleration, as we talked about in kinematics, is going to be measured in meters per second squared. Now we need to talk about some types of forces in order to understand exactly how these interactions can happen. So first we have contact forces. Contact forces are forces where the interactions happen because of a touch of two objects. The objects actually come into touch with each other, and thus that action-reaction happens. We have our F equals ma, and we can say that objects will move, not move, will change their acceleration based on what's happening there. A non-contact force does not require an actual touch for the interaction to happen. Some examples there: magnetic force, electric force, the gravitational force, all of these very important, but you see some examples of both. The most common is going to be contact forces, although we say that as far as what we'll look at in physics, the most common really is happening all around you right now is gravity, which is a non-contact force. And so to look at a couple specific examples of these, we're going to move right to gravity right away. Gravity and normal forces are the first interaction I want to look at, where gravity pulls down, and then this weird term, the normal force, and I think that's a new term probably for most people and it's something very different, applies really to a reactionary force that counteracts gravity. The reason that this object sitting right here on this table doesn't fall through it is because there's a support force provided by the table that keeps it standing up and keeps the object on top of it. That is known as the normal force, and it will be true for all objects that are sitting around that are not being pulled to a center of gravity. So everything on the surface of the Earth has a normal force pushing it back up to keep it from pulling through the surface of the Earth. The next one I want to look at are tension forces. And tension forces are very interesting because they can only happen towards the center of the object that is in tension. So we see right here this interaction happening. Let's say this hand is holding this object of mass m up. This object has a weight or a force of gravity that's pulling downwards, and then there is the rope in between that's supporting it. That tension force is going to be the support force in this case, and it's going to be equal and opposite because the rope is not compiling up on itself as this person is holding onto it, right? It's just hanging there while they hold on to this block. So you're going to see that it's going to be equal and opposite there, and then we see the free body diagram for the actual hanging object. If the object is not moving, then tension and weight will be equal and opposite, as you see there in the diagram. Those vectors are of the same length. If it is moving, then that hand would start moving upwards, the tension force would become greater, and there would be some acceleration in the positive y direction. Okay? Last one I want to look at right here are spring forces. Spring forces are going to be forces that happen because of some sort of elastic object, oftentimes an actual coiled piece of metal, as in a spring, or potentially a rubber band or some other object. They could pull backwards and have an elasticity to it. That elasticity is represented by a constant K, and that is going to be measured in comparison to how far the object is actually displaced x. So if I were to take a spring and pull it outwards, x, that distance outwards that I had to pull it, times that spring constant, would give me the actual force applied by the spring to pull back inwards. And the fact that it's pulling inwards, or opposite the direction that I'm pulling outwards when I expand the spring, is why there is this negative in there. So that is important. Whatever direction I pull a spring, or I push in on a spring, it's pushing the opposite direction, and that's why there's a negative associated with that equation. Potentially the most confusing of all of the forces is friction. Right? Friction is a reactionary force and only exists because of another force happening. So we've got this little guy over here, and he is pushing. He's got some applied force Fa to the right. But you see the rough surface in the bottom on the ground there between the bottom of the object and the ground. And I think this picture shows that really, really well, how rough that surface can be. The rougher it is, the greater the friction force will be. And that's really what's happening. The reason your hands warm up when you rub them together is the friction of the tips of your fingers and the palms of your hands moving against each other. That same thing's happening. It produces thermal energy. So friction is something that happens whenever objects move past each other. And there are two types. The first being static friction. Static friction is the force required to move an object from rest. The reason you can't just push a car and have it start sliding along the ground is because there's a lot of static friction between the rubber of those tires and the road. So it's the force required to move an object when it is at rest. Now, once it starts moving, there's kinetic friction. It's going to be easier to keep it moving once it begins moving than it is to start moving from the very beginning. Okay, that's always going to be the case no matter what. We represent how we calculate this using our F here, our force of friction. It's going to be equal to mu, a coefficient of friction that represents the roughness of those surfaces as they move past each other, times the normal force. And a reminder, the normal force counteracts gravity. And the reason we don't just use gravity is because there are potentially other forces at play here. And so if you were, let's say, pushing down on a lawnmower as you move along, that force of the push adds additionally to the gravity, and thus is going to make it harder to move because of friction than if you weren't pushing to some degree downwards. Now, to look at the different coefficients quickly over here on the right, I purposely left the names off these because I care more about the comparison that you can see here than the actual objects that it is. There are an infinite different number of coefficients of friction. It totally is just going to depend on the roughness of the surfaces in contact with each other. Every single surface on the planet could interact differently with every other surface on the planet. And that's why we've got coefficients of friction that are going to vary greatly based on interactions. Okay, you will see here in this table that the static coefficient of friction will always be greater than the kinetic coefficient of friction. These are tested and considered to be held true for these objects that are shown right here, and that will always be the case. Static friction will always be more than kinetic friction, and thus the static coefficient of friction will always be greater than the kinetic coefficient of friction. Moving on here, I want to talk about vectors and finding net force real quick. So in order to determine how these forces cause an object, a mass, to accelerate or not to accelerate, we need to be able to find the net force using our vectors. If you go back to the Unit 0 video that I've made, it does talk about vectors a little bit more in that, but we're going to do a quick summary right here. If we look at situation A right here, I have no net force acting on this object. I've got 3 newtons up, 3 newtons down, 5 newtons right, 5 newtons left. They all equal out and will cancel each other out. So there's going to be no net force, and thus with no force, that mass will have no acceleration. 0 equals m times 0. In situation B, we're going to have a different scenario because despite the fact that the top and the bottom forces will cancel each other out, I do have a net force to the left here, so friction will be pushing backwards. Now this is an impossible situation because friction can't exist without an applied force to the right, but it's worth noting here just because of what's shown that there would be a net force to the left. Situation C, up and down, same thing there. So we're going to have no acceleration happening there whatsoever. And situation D would be similar to that the hand that was holding on the rope and the hanging mass earlier that we saw, if we started moving upwards there, we could have this applied force of 40 newtons. There would be the force of gravity pulling down at 25 newtons, and thus we would have a net force of 15 newtons moving upwards, causing some sort of acceleration. Now, these first examples were really easy because they were just in the x and the y direction, but if we see something like over here on the right, where there are applied forces at angles, it's going to be a little bit different to figure this stuff out. What we're going to have to do is sum the forces in the different directions that are present. So we would have to find forces here using this theta angle that would be given of F1y and F1x, and then the same thing here, F2x and F2y up here, and then use F3, which is just in the x direction, and put all those together to find the net force in the x direction and the net force in the y direction. All right, that's going to be really important when we look at MA versus the F equals 0. Okay, so there's two different scenarios we could get here. And I love this Dwight meme real quick because it's just that KISS. Keep it simple, stupid. KISS. Great advice. It hurts Dwight's feelings every time, but it's really important for what we're looking at here. There are a couple very easy steps that we can use to keep this simple to determine whether or not there is acceleration of an object using our F equals MA. So step number 1 is going to be sum the forces in the x and y direction, just like we were looking at down here. Okay, I'm going to take F1x, F2x, and F3, and I'm going to say I've got to have a force that's positive in the x direction because they are all moving towards the right in the positive x direction. I have F1y and F2y. One is positive and one is negative. I'm not sure, based on what's given here, whether or not we will have a force in the y direction. I can guarantee that it's going to accelerate to the right, but I cannot guarantee yet whether or not it would accelerate up or down until I combine those forces. That is the first step that we need to do. Once we've checked that off, we're going to look and we're going to say, all right, option 1, forces combined to be 0. Okay, for first example, we're going to say that's the case. Forces combined to be 0. Let's say that F1y and F2y are equal to each other. They were opposite in direction. They combined to be 0. This is going to tell us that we're in equilibrium and there's no acceleration. This implies that there's no acceleration in the y direction, and so that mass would not be accelerating upwards or downwards. Okay, in the case of what it looked like right there, it's going to be moving along the ground then, horizontally to the right, but it's not going to move up and down. Now, this does not always mean that the mass is going to be stationary. If an object, let's say a car, was on the highway, it was moving with cruise control, then the velocity of the car would remain constant. It's still moving even though it's not accelerating, and that's important to note, so make sure we're noting that as well. Now, to go back here to our second option, the forces do not combine to be 0, which was our option in the x direction before. So we're going to go down that path next. So we had a total force in the positive x direction because the forces did not combine to be 0. This means that we have an applied force and that the mass must be accelerating. So the velocity is increasing in the positive x direction based on our previous example from this slide right here, positive x direction. And this guarantees motion. Okay, it may have started at 0, but it's going to increase velocity because there is a positive acceleration, so it guarantees motion to some degree. That's very important to note, especially when we look back at our kinematics. All right, next thing to look at here are force diagrams, and they're exactly what they sound like. They're diagrams of forces. So if we look at our rocket up here first, we see, okay, there's some thrust force that's pushing a rocket upward, and it's from the fire coming out of the back of this rocket. Now, there's a couple things that are counteracting that. First, the weight of the rocket is pulling it downwards and kept it wherever it was to begin with, but also drag, right? There is some sort of drag here. Typically, we will ignore air resistance and other drag forces, but it is important to note that that could be there. If this thrust force is great enough to overcome weight and drag, then we will have a greater force in the y direction, a positive force in the y direction, and acceleration in the y direction of this mass. Now I want to look at the car at the bottom because it does a great job of showing different scenarios of what's going on. I mentioned a car moving with constant speed or on cruise control on the highway, and that's what our first example is here. We see gravity and the normal force here, pushing up and down, are going to be equal. Car's not lifting off the ground. That's a good thing. All right. Now we say the thrust force, the force of the engine of the car, the force requiring movement here, forward, you see the length of that vector as far as friction moving backwards is the same. So even though the car is working to keep the engine running and the car moving forward, it is the same amount as the air resistance of all the air hitting the front of the car and the friction of the tires and everything else that's pulling it back, and so it's moving at a constant speed. If we look at this second example here, we hit the gas, and now we're moving forward with an increasing velocity. We're accelerating in the positive, in this case, in the negative x direction, and so we have a greater vector showing that acceleration forward of the car. And then here for this last one, the opposite is happening. We've accelerated too much. It's time to hit the brakes, and now we are slowing down. And so you see the greater force vector in the negative direction there, in the opposite of motion, that is slowing it down. All right, from there, we have force diagrams. Now we need to talk about free body diagrams. And this first diagram up here at the top is really, really helpful to look at this. All right, we have a force diagram here that shows the object and the force applied to it. All right, and really all it's telling us right there is, okay, we have this 15-kilogram sled, and it's being pulled with some force, some applied force, at a 30-degree angle from the horizontal. All right, now that's all that's shown there on our force diagram because we have our object and the force that's applied. But if we move over to our FBD over here, our free body diagram, then we have removed the body from that. We've taken away the sled, and we're just showing a point with the forces applied around it. And now we're accounting for things like its weight downwards and its normal force pushing upwards. And if we take that even to the next level here from B over to C, then we're taking that P, that pull, that applied force at 30 degrees, and we're breaking it down into its X and Y components using our vectors. So this is what we have when we have a free body diagram. Again, remember, it's free of the body. Okay, so we would have just a representation of something happening here on the left at the bottom, and then we have a force of the Y applied to keep it up, the weight of the person here, the weight of the ladder that this person's standing on, a friction and a normal force down here at the bottom, all of the forces applied on the free body diagram as opposed to the simpler force diagram. All right, there are two very specific examples that I do expect you to see practice problems from here, and I'm going to show you a little bit about how the tricks to making these work. So first thing we've got here is what's known as an Atwood machine. Really, it's a pulley with two masses hanging on it, okay? I'm going to say that M2 is greater than M1. So thus it has a greater weight and a greater force of gravity, which means FG2 here is going to be big and FG1 there is going to be small. You see the difference in the vectors. This implies we're going to have M2 moving down and M1 moving up because one is larger than the other, and that's how a pulley works. The important thing here is that we make the direction of motion positive. So everything then in this direction on this side will be positive because it's moving upwards, but everything on this direction on this side will be positive because it's moving downwards. So FG2 we would consider to be a positive force. FG1 we would consider to be a negative force because the direction of motion is what we consider to be positive. You might also see a hanging block problem. Well, let's say this mass right here is more massive than this, despite how it looks right now. All right? This implies then that there's going to be motion in this direction and thus motion in this direction. So we're going to make this positive and this positive. And I want to look real quick at the weights of both of those objects then. This means FG for this object right here is going to be in the positive direction. But because FG here would be downwards like this, it's not something we're going to use as far as summing the forces in the direction of motion and finding acceleration because it's not in the direction of motion. This would likely just counteract the normal force that would move up, and we're going to ignore those. There'd be a tension force pulling this forward and potentially a friction force hindering that motion, and that would be it. And you'll work a lot of these types of problems as part of your practice for this. I'm going to show you one more part of this with an Atwood machine real quick. So I'm going to flip over to our simulation here. Shout out to the physics aviary where I got this simulation from. But I want to go ahead and say, okay, look, I've got my masses being the same now. I'm going to start this simulation. We're going to notice there's no motion. And if I scroll down some here, I've got this great position time graph, and you see the line increasing here, position's not changing. And the same thing here with the velocity time graph, the velocity's not changing. It's all zero, it's all stationary. Now, if I reset this, and let's say I up this mass and lower this mass. Now I have a greater mass here and a lower mass here. And if I start this right away right there, boom, we've got motion very quickly. And you see here on our graphs. The position greatly changed, and that curve, as you know from kinematics, implies an acceleration, and we had a constant velocity as this happened also. You see the steepness of the curve? Well, if I reset again, and I put these much closer to each other again, we should end up with a curve, motion that's slower, still an acceleration happening there, but we have a curve much less steep. The position changed, there was still an acceleration shown by the curve here, and we see that there was still some velocity, but it just didn't happen quite as much. Okay? So flipping back over finally to our last slide here, a reminder that force drives motion, and that's why we did kinematics first and dynamics second here, okay? With no force, we've got our situation where a body at rest will stay at rest and so forth and so on, Newton's first law, and so thus there will be no change in motion. This is why you've probably heard an object in space, if it were moving forward, it's going to continue to move forever until it interacts gravity or some other force. Now, if there is an applied force, then F is going to equal ma, and thus we're going to have a change in motion. So that object in space that's just moving on forever, once it hits maybe a gravity well, a black hole, a different planet, a sun, something like that, that's going to pull it towards it, and thus there will be a change in its motion. It will speed up, it will slow down, it will break apart, whatever's going to happen. Both of these are still governed by the kinematic equations. And that's really important to note. We're not forgetting kinematics with what we're doing here. We're building on it by adding dynamics to it. So that's it. That's what I've got for today. Thanks for being here.